So good morning. Welcome to Krishna's classroom. We start with another episode of Riemann integration, a continuation of the previous talk. In fact, if you recall, we concluded last lecture with a statement of a theorem which I have printed on the board, which is equivalent to the definition of F Riemann integrable, or it gives a number of conditions which are equivalent to F Riemann integrable. If you look at read the statement of the theorem, then it says the equivalence of three statements. In the first statement, so essentially this is what it is. 1, if and only if. 2, if and only if. 3. This is the statement that you need. And the first one is the definition of the Riemann integration, which says that you have the upper integral, lower integral existing, and the question is whether they are equal. If they are equal, then you say F is Riemann integrable. So the fact that they are equal, if you assume they are equal, then it is equivalent to this statement. Now, what is the importance of this statement? What is the use of this second statement? The second statement, if you prove the second statement to be equivalent to the first statement, then you can actually make use of the second one to prove that, test whether a given function is Riemann integrable or not. So also the third statement in a slightly different form. So I am not going to prove that this theorem completely, but possibly show the first part, namely 1 is and only if 2. I think I have made some comments about this towards the end of my lecture. So I just start taking it up. Now see how the proof goes. Now this is the important part. It is not the fact that is proved there, but a mathematician or a student of mathematics should be essentially look at critically the way in which the arguments are put forward to prove a theorem. And you have to learn the art of proving theorems, the art of speculating results, which and then possibly working out a proof of it. So that is the important part of creative mathematics. So you are all getting trained for this particular purpose. Therefore, it is not merely storing some facts in your mind about Riemann integrability. Okay, let us see what this means. So let me just look at the proof of 1 implies 2. So when I will do it a bit elaborately so that in future scenarios this is essentially the pattern that you have to follow. What does this mean? So what is that you assume? There should be clarity about this. Assume. Okay. And what do you prove? Prove these are the two things that you do. So one should be clear about what exactly you assume, what exactly you prove. Okay, what does the first statement say? The first statement says that you have the following. See, it says that small m into b minus a is less than or equal to what? ULCF is less than or equal to the lower integral a to b And the second part of it is this. Because we have assumed 1, therefore the equality is there. So this is equal to integral a to b, the what you call the upper integral of fx dx, which in turn is less than or equal to this is what you have. And this is true for every p belonging to the set of all partitions of capital P. This is the result that you have. Now from here you have to get here. Now what is the advantage? The advantage is that you know that UPF and LPF are essentially finite sums that you are working on. Therefore it is easy to compute. And they are associated with what? The lower approximation by step functions and the upper approximation by the step function. So it's quite easy to compute what they are. So what we are saying is that rather than, if you look at this statement, what is this? This is essentially the least upper bound of all LPF. This is the greatest lower bound of all UPF. So more sophistication is involved in this. Whereas in this statement, no such sophistication is there. So how do you prove this? You have to assume this, and from there you have to get that. So what is the meaning of this? So let me just call the lower integral of fx dx equal to some alpha equal to the upper integral of. Now this is nothing but the supremum of LPF, and this is nothing but the infimum of UPF, which means the supremum of LPF and the infimum of UPF are equal. What does it mean? It means given epsilon, there exists a P belonging to P1 belonging to P plus alpha minus. This is possible because it is the supremum. Okay, here it is the infimum of UPF. So using that statement, you can prove this. You immediately get this. From the other part of the statement, this is what you get. There exists P2 belonging to P such that U P2F minus alpha is less than epsilon. So you have the existence of P1 and P2 guaranteed by the assertion 1. Okay? So what do you do next? Now you see that just a category, we have not got the P. We have got only a P1, a P2. And our statement is that there exists a P. So what do you do? See, you look at this one. So you want to construct a P from this P1 and P2. Is it possible to do it so that the same sort of inequalities work? You see that if you have a P1 and P2, both are partitions of the interval AB, then P1 union P2 is a refinement of P1 as well as P2. P2. So call that P. So set P equal to P1 union P2. Now, if P is a refinement of P1, then this is what you have. You have, which implies L P1 F is less than or equal to LPF. And so also U PF these are the properties. Therefore, if I use P, I can rewrite these inequalities in the following form. How does it come? Now you see that alpha minus LPF is less than epsilon by 2. UPF minus alpha is less than epsilon by 2. So with this and the property of refinement, that these are the properties that you have. So you get the following. So I just take out this. So what one gets is the following. So you get LPF is equal to this is less than epsilon by 2 plus. So there you are. So we have shown that 1 implies 2. But our statement is something different. Our statement also includes another part, namely that 2 implies 1. So how come to some kind of a, it's all about techniques of proving physics. So this is what we want to prove. 2 implies 1. That means we are assuming assume 2 and then prove okay. What do you assume? What you assume is that there exists a P such that UPF minus LPF is less than epsilon for a given epsilon. So for a given epsilon, this is true. Okay. Now you want to deduce 1 from there, which means the infimum or the supremum of LPF over P, all partitions P, is equal to the infimum of UPF over all partitions P. This is what you want to prove. Okay. Now, usually we make an observation. When you say 2 is equivalent to 1, 2 equivalent implies 1 is equivalent to what? Not 1 the negation of 1 is equivalent implies negation of 2. Why it happens now? If you want to be familiar with what it happens. P implies Q if and only if not Q implies not P. How does that come? Let us see. If we just use little bit of Venn diagrams to explain this. Okay? We are making a strategy to prove it. Okay? So let me write capital P as the set of all x which satisfies Q you define as the set of all x for which x satisfies Q. So in the Venn diagram, what is it actually? P implies Q means capital P is contained in Q. That means you have a universal set U in which both P are placed. Then you have P here. So that whenever you are here, you are already in the set Q. That's what it says there. Whenever you satisfy all the conditions to be in P, you also automatically satisfy the conditions to be in P. This is the meaning of it. Now, you see that this whole picture tells you the following. You take, what is the status of Q complement? Q complement is this one. Is contained in P complement. So P contained in Q if and only if Q complement is contained in P complement. Now you know that Q complement is Q. So using that you see that P contained in Q is equivalent to Q complement contained in P complement. Therefore, if you want to prove 2 implies 1, you prove that the negation of 1 implies negation of 2. Okay? So let us start working on that. Suppose one is not true. What is the statement? Several things. The statement 1 says that the upper integral is equal to the lower integral. Okay? And you know that the lower integral is always less than or equal to the upper integral. Therefore, suppose this is not true, then what it says that is integral a d, the lower integral of fx dx is strictly less than upper integral of, that's the negation of the statement that f is not Riemann integral. Okay? So let me call this two numbers. Let me designate this as alpha, designate this as beta. So it says that alpha is strictly less than, this is the statement. Okay?